So, this chapter is about acids and bases. Okay, acids and bases neutralize each other like what? Excuse me? Little high school relationship.
She said she's an acid.
Yeah.
I didn't hear the talk.
Okay, so.
You know what it's all
Is this
about.
chapter a little bit harder?
The last chapter?
No.
No, but it's still hard.
Who is that Megan Trainer from like 2009?
What?
Okay, so obviously we live in a world full of chemicals, and you have probably heard acids and bases before. Yeah?
Yeah.
Okay. You probably don't know necessarily what they mean. You probably just attribute it to, oh, acids and bases do nasty things. Sometimes they do very little. Bases are nice.
Bases, you know
Why
why
say that?
bases nice?
Because if you have
No, it's not.
like an
Your
acidic
car?
stomach, bases are good.
Yeah, like taking Tums.
Yeah.
Yeah. But drinking a basic solution would equally do damage to your stomach as. Alright, so we're going to kind of talk a little bit about kind of the history of what they thought about acids and bases and how it's progressed to where it is today, and some definitions of how we define acids and bases. So, let's talk about. Ooh. I don't know why that's in there.
Oh, booger.
Is that like, do that again?
Oh, booger.
Oh,
I guess it's a bummer to have sour taste.
What? It's not bummer.
Alright, interesting. Okay? Now, I have really old litmus paper that doesn't work. So, and honestly,
Oh, go get some from Zaffer.
the litmus paper test is really a completely outdated test. The reason why I say that is you can just use a pH sensor to figure out what the pH is.
Try it.
Yeah, we'll have a lab this chapter, I think.
I do that a lot in the summer.
What?
The pH test.
For what?
And some people take
Oh,
it.
litmus paper?
Yeah, so when you stick some of
Yeah.
that paper in there,
See
and
if it's, yeah.
sweet color. And some people taste it, and some people can't.
Yeah, I would.
Oh, that thing that was so
Taste
good.
or non-taste. Pinchot?
That's
Yeah, you're
no, that was
taking
not
it.
acid base.
Oh,
That's
it's bio.
just like genetics.
Yeah, that was
pH
just.
is
if you have to-
base, right?
Oh, pH, the
It's
pH
not whether you
scale
have
is
taste or
both.
not. It's whether you can
Depends on
taste
where you're
that.
at, where you're at on the pH
It's
scale.
your taster.
Okay, so,
Yeah, whether you
Um,
can taste that chemical.
we're actually gonna use just the regular pH probe, pH sensor. There are a variety of ways to figure out pH. The reason why the litmus paper is kind of outdated is, one, the litmus paper could be going bad, and then it won't change colors like you had hoped. And two, the litmus paper will just tell you whether it's acidic or basic, not how acidic or how basic, unless you use specific litmus paper, which turns different shades of color based upon what the pH is.
We have our handles at Fairway when we have to check
Yeah.
the sanitizer and stuff.
Oh, really?
Yeah.
You had the pH paper that was like, it had one color for a pH of 1.
Yeah, it
and
started
2,
out
3, 4.
orange, and then when you rip it off, it put it in the thing. If it was like 300, it would go like a dark green. If it was like 400, it'd be like yellow.
400? Yeah, I'm assuming you mean 13 and 14.
Yeah, 400. Or PCM, the product.
Oh, okay. Yeah. Yep. So usually, like they do have like the complicated litmus paper where like a pH of 1 is like a really light color, and then as you go up in the pH scale, it becomes darker. So like starts out like a really yellowy, and then it gets to an orange, a darker orange, and then a red, and then into the green, and then a darker green, and then a blue, and then a darker blue. Is usually what it looks like. Okay? But even then, you still, like when you see it, you kind of have to like, oh, well, it's kind of in between these two colors. And so it might be a pH of 8, it might be a pH of 8.5.
Just looking for you. Oh, sorry.
Are you supposed to be hurt?
Oh, no, it's a send-off. Well, I'm a TA.
Okay. So. Okay, so it says reacts with active metals above the activity series. I'm actually going to ignore this. I don't think it's that important. So you want to cross it out in your notes, you certainly can.
Wait, what?
Is it in your notes? No,
Yeah,
it's in
it
your
is.
notes.
So,
There goes a half your chemistry book.
it's gone.
Okay.
We don't need that side.
We don't need this side anymore.
Well,
Wow.
the next year's student will.
No, they don't.
I don't know what you're talking about.
Alright, have you ever heard of an electrolyte solution?
Yeah, like Gatorade.
Okay. You guys have all heard of probably Gatorade, Powerade, those things. They're like touted as
Pickle
this,
juice.
like super electrolyte solution. Actually, they're actually really weak electrolyte solutions.
Pickle juice is better.
Yeah. What's up? Question? Oh, it's probably random.
Does banana pepper juice have the same like?
Probably. I don't know if it's exactly the same.
I'm drinking that.
I actually, one year, I read a big article, because it was like a couple years ago when LeBron had like those major cramps in the finals. I don't know if you guys watch basketball and you know what I'm talking about.
Gatorade.
And so they were doing some research as to why, you know, he was cramping, because he was having these legit cramps. They weren't just like your typical cramps. These were cramps that were like shutting him down. And there was another guy in like the D League or something that was having what LeBron was having, but like way worse. Not way worse, just it like started earlier in the game. Like he could only go through like 3 quarters, and then in the 3rd quarter he would cramp up and then be done for the game. Well, they found out, they did some tests, and they found out that he got in his sweat released like way more electrolytes than the average person. And so because he lost so much electrolytes, he didn't have that in his blood, and so what happened is he cramped super bad. And so what they had to do is like they had to basically he had to drink salt water during the game to be able to replenish all of.
What, doesn't that just dehydrate you?
It
But it
dehydrates
gives
you, but it
you-
gives you electrolytes. So you would have to probably do both.
So round noodles have electrolytes.
I don't know what's wrong. I don't know that answer. But what they found out is LeBron has something similar to that, just not to that extent. He just, when he sweats out more electrolytes than the average person, and so they've had to change how he's hydrated during the game, which is kind of interesting that they had to kind of use science to be able to figure out, yeah, this guy is losing too many electrolytes, and we've got to find a way to replenish it better than Gatorade and Powerade, which actually, if you do some studies, they don't really have that many electrolytes in them at all.
Is it better than just water though?
Better than just water.
But it tastes
Like I've done light bulb tests where you put a light bulb in a solution that has a lot of electrolytes, and the light bulb will be really bright and turn on really high.
That's awesome.
But if you put it in a Gatorade solution, it's like barely noticeable. Like you can see the light on.
Can we do that experiment?
If you bring in Gatorade,
Let's do this chapter.
sure. Bring in Gatorade or Powerade, we'll do it.
I actually
What
have.
else could we bring
Bring your
in?
mix.
We don't have probably time today. Well, we'll see if we have time
What else
today.
could we bring
Why
in?
not has high electrolytes?
I'll just make a salt solution.
I have Gatorade in my
I
locker.
don't think
We'll try banana
like
pepper
juice
juice.
like that with more.
I have Gatorade and Powerade in my locker.
I don't know. Because probably the average person doesn't need that much, and there's a point where you can have too much.
That's
Like
Gatorade?
you don't want to be just drinking salt water, that would kill you after a period of time. Like if you just drank salt water, you would create what like a hypotonic, I think is what it's called, where you would have so much salt or electrolytes in your bloodstream that it would cause, I can't remember if it would cause water to either go all into your cells or come all out of your cells, which would either cause them to explode or shrivel up. And so you don't want to have too much electrolytes. It has to do with how diffusion works, and usually what will happen in that semi-permeable membrane between your cells is the water will go in because it has to account for all of the excess salt, and then you either will have it explode or shrivel up depending upon, I forget the word, like hypotonic and something. It's how dialysis works, using osmotic pressure and things like that. Kind of interesting. But anyway, take advantage of chemistry, we'll talk about that. What?
Gatorade in my locker.
You No, I don't think we have time today. Okay, but basically what an electrolyte is anything that will cause electricity to conduct. Okay, usually any salt that's dissolved in water will produce an electrolyte solution. Okay, acids are by nature electrolytes because they produce ions. Acids and bases do. Okay, so that's why you're seeing electrolyte here, is because when we start talking about what is an acid and what is a base and what happens, we're going to be doing a lot of ion stuff this chapter.
So when you put a light bulb in a substance, does it take out the electrolytes?
So what I have is it's basically just like a light bulb connected to a cathode and an anode, which basically, like if I plug it in to the outlet without anything, it's a open circuit, so current can't flow and turn on the light bulb. But if I put it in a solution that has a lot of ions, the ions carry the charges from the anode to the cathode and close the circuit, which allows current to flow, and then the light to turn on.
Don't water closed circuits too?
No, it doesn't have ions in it. It doesn't, I mean, it has some ions in it, but not enough to notice the light even on.
So what in water causes it to short electricity? Short out, like if you get a wire and put it in water and short it out?
Because there is some ions in it that it'll allow electricity to pass through it. But we can't notice it with that experiment because the light bulb doesn't, it probably is on a little bit, but our eyes can't detect it. Basic properties.
Wasn't favorite?
What?
Go back. What is going
Wasn't favorite?
I don't know what that means. So they used to be able to define acids as they're sour. I wouldn't recommend figuring out if something's acidic by tasting it. I also wouldn't recommend tasting a base. Can anybody think of a slippery thing that could potentially? Oil. I don't think that's base, but it's a good idea.
It's not like baking
Alive.
powder
Grease.
or baking soda. That's what I'm thinking.
Baking soda is
It's
a base.
like-
I haven't really. Well, it has to be with
I
water.
know, I was
or-
thinking
or-
of the taste.
Oh, really? Bitter? Okay.
I think. I mean, I've never straight up tasted it, but.
I don't want you guys to think that everything that is slippery is therefore a base. And that's why, that's why this is not the greatest example of defining an acid and a base, right? This is what they came up with before.
Jello.
Yeah, we'll get to that. Yep. But actually soap is a base.
Pudding.
Grease?
I don't think grease is.
Pudding.
I don't know what pudding is or not. I really don't know. Okay, so we're starting to see the problem with using just slippery and sour. Okay? And yes, this would do the other thing. It would take and turn litmus paper blue. Okay. So, what acids and bases do to each other is they neutralize each other. So, if you have, this is exactly why if you have heartburn, you take Tums, because Tums are any antacid. It sounds what it is in the name. It's called an antacid. What do you think an antacid is?
Acid.
Which would be a base. Okay? So acids and bases neutralize each other. So what you do is you take an antacid tablet to help neutralize the extra acid that you have in your stomach. Okay, well actually not your stomach, it's usually in your esophagus. And usually people think that you get heartburn from eating spicy food, and it has nothing to do with the spicy food.
You get heartburn when you eat too fast.
Or eat too much. Because what happens is your stomach has hydrochloric acid in it. If you eat too much, the hydrochloric acid rises, can get up into your esophagus. And I promise you, there's nothing you eat that's going to burn more than the hydrochloric acid in your stomach. So, now what's interesting about neutralization reactions, if you have equal strength acids and bases, what you will get out of it is things that are harmless.
All we talked
Oh, we
about
did this in
this.
physical science.
Acids and bases, when they neutralize each other, it gives you two products that are not harmful at all. Which can be, there's some significant uses for acids and bases that we will find out and talk about later. Okay, now you won't know because I haven't defined what an acid and a base is, but this is an acid, this is a base, and we know that this is what?
Salt.
Table salt, right? It's the salt we eat every day, right? Here are some other common acids and bases that we you may have seen or experienced before. Vinegar is an acid, it's acetic acid. You're like, well, I drink vinegar,
What?
right? Probably eat vinegar sometimes.
Oh.
Yeah, vinegar is not, you're probably like, well, so you're saying I drink acid? Yes, you guys do. In fact, your water that you drink is either acidic or basic. Our bodies can handle a certain amount of acidic stuff and a certain amount of basic stuff. Okay? It's a myth to think that we can't eat acids or bases because your bloodstream is acidic.
Wait, so how much would a light bulb light up in like sauerkraut?
How much would I like to?
I don't think if I just touched sauerkraut it would work that way.
Like the sauerkraut juice and stuff.
Oh, I don't know.
How much would it light up your blood?
I don't know. I haven't
Let's find
like
out.
pricked myself.
Find out.
I don't know. Okay? Vegetables or your vitamin C is actually an acid. Okay? The carbonic acid that they put into your soft drinks is acidic. Your pop.
Soda.
Because they don't have.
A lot of your fruit has acids in it. If you play basketball a lot, your muscles get sore because it produces what? Lactic acid.
They burn.
Okay?
Not in your mouth.
Okay, you put that.
Bee venom, sour milk, rhubarb. There's a lot of different things. The last one here is a base. A lot of your cleaning supplies in your house are bases. Your toilet bowl cleaner is a base.
Don't eat that.
Yeah, no, don't do that. You don't have to put any of this stuff down. I'm just kind of giving you some understanding that acids and bases are everywhere. In fact, it probably is the most common chemical that you would have heard of or experienced on an everyday basis outside of like, you know, carbon-based things in water. Alright, batteries are actually acids. They have acids
Wasn't
in
it
them.
Gage who was licking the batteries?
Battery acid will kill you.
9-volt batteries, you like make it to see if you have.
I know, you told us that. Right, milk and
Is that
magnesium
because your
oil.
saliva is acidic?
No, it's because your saliva is a solution. It's got iron.
Battery acid will keep you.
Okay, well then. Okay.
Yep, so it allows current to flow and close the circuit, so you'll feel it, obviously, as it goes through your tongue. But it's not like a high enough, like, doesn't have a strong enough voltage to
So like
really.
hurry.
Yeah. Like if you licked an outlet, that's a different story.
Maybe.
Okay, the first definition of an acid and base. Okay, listen. We're going to talk about 3 different definitions of how to define acids and bases. The first was the first one that came about. It has some limitations. Okay, we'll talk about those limitations. The second one I'm going to give you is the one we're going to use the most, even though by its definition it doesn't classify every acid and base. And the reason why I use the second one instead of the third one, which actually classifies all acids and bases, is because the third one is far more difficult to understand and it only adds the more complicated acids that we'll not even talk about anyways. So we're going to focus most of our time on the second method. However, the first method has some advantages too. It's called Mr. Arrhenius. Savante was his name. I love that name. I'm going to name my next child Savante. Savante.
That's
How do you
not what
spell
it's
that?
I don't know.
Savante. S-V-O-N-T-E.
That is not
S
what it is.
V. I got it here.
That's very Swedish.
A-N-T-E.
All Swedish.
Savante. Okay? Alright, so he was the first to kind of define an acid and base, and he actually did a pretty good job of it. We'll talk about what is really the main difference. So, an acid is something that when you put it in water, it gives off a what?
Positive.
Hydrogen ion. Okay? Now, what you're going to find, well actually, I'll tell you. A hydrogen ion is really just a proton. Like, if I have a positively charged hydrogen, that means I lost 1 electron, correct? Well, how many electrons does hydrogen have?
Does that have a new?
It depends.
1.
It only has 1 electron. So if you remove the 1 electron it has, really you're just transferring transferring one proton and potentially a neutron with it. Okay, but the neutron isn't going to really do a whole lot. Okay, so his definition was, now does this mean everything that has a hydrogen in it will be an acid?
No.
No, it means that if, when you put it in water, it gives off one of its hydrogens, that's how we define it as an acid. Not that, oh, it has a hydrogen in it, because there are a lot of hydrocarbons. That's not an acid. You put that in water, it will not break up and give off a hydrogen ion. Okay, in fact, this guy won't even probably dissolve in water because it's non-polar. Okay, so for something to be acidic, you have to have it give off a proton or a hydrogen ion. Okay, and actually you'll find that the definition of Svante Arrhenius and our next definition for acids are exactly the same. The difference is in the bases. Okay, so in a base, based on Svante Arrhenius, he said that it gives off OH minus when it's in water. Common example is NaOH. When this dissolves in water, it will give off the OH minus ion. It will break up into its ions. Remember last chapter we took things and we broke them up into their ions. Okay, when this breaks up into its ions, it will look like this. So what does it give off? It's OH minus. Now the reason why they say that is basic is because if you put this with an acid, like say HCl, when it breaks up into water, do you see how the H plus and the OH are going to react with each other to produce a what?
H.
Salt.
Water.
Water.
Nice. And salt. Wait, NaCl.
Yeah, and salt, but I'm specifically saying the H and the OH is what's going to produce your water.
It's not water.
Now, the reason why this isn't a great method is because there are things that do not have OH that act as a base. So, okay, so I already kind of told you this, not every substance that has H and OH are necessarily an acid or a base. I gave you the CH4 example. The one on the right has an OH minus in it, but it does not act like a base. It will not give off that OH minus when it's in solution or when it's in water. Okay? So this is the definition we're going to spend most of our time talking about and using. The Bronston-Lowry definition. And what you will find is the acid definitions are virtually the same. It says it donates a proton or protons. What do you think is the form of the proton?
H.
H plus. Okay, so really there is no difference between the definition of acids for the two that we've talked about. The difference between these two definitions lies in the base. Okay, what does a base do? Accepts a proton. Now, a lot of times, that's a result of having an OH in it, but not always. For example, this guy is actually a base. Because when you put it in water, it will take a hydrogen from water. And what does it give off? What is the result?
Ammonia.
Well, this is ammonia. This is ammonium ion. But do you see how here to here, what happened? They
Took a proton.
gained a proton, right? Okay? So, what happened from here to here?
Lost.
Lost the proton. So I would define this as a what? And I would define this as a acid.
Water's an acid.
Water can be both.
Wait, so water's in
So acid and base isn't necessarily like a category or something. It's just whatever
What
its
it does.
function is.
For example, if I put a acid in water, water will act as a base.
Oh.
If I put a base in water, water will act as an acid.
But there
And there are some other substances that will do the same thing. Those are called amphoteric substances, which means they could do either depending upon what they're with.
What else does that?
H2PO4. There's a bunch of them.
Crazy.
But water is the most common. What?
Isn't that crazy? How something like so like, oh yeah, water can be a base and acid. You know, but if you think about it, water's the most abundant.
Water is so unique. I mean, just even talking about things like surface tension on water, things like why solid water is less dense than liquid water, why water has such a high specific heat capacity. We talked about that this year. And now we're talking about water as the ability to be an acid or a base. Water does a lot of cool things, and I think we don't think water is awesome because we see it every day. But if we like never had water and then found it and started studying it, we'd be like, wow, this is the coolest thing in the whole entire world.
So why don't for energy they just stick one of your contraptions in the ocean and take all the electrolytes out of it?
No, that's not how that works.
Why not?
When I plug it into an outlet, so I'm getting the electron. It's not taking the
You made it sound like at first that you were just sticking a raw light bulb.
Okay, yeah, I realized
I was like,
that.
I'll
I didn't know-
get home.
I'm sorry. I thought that maybe I had shown you it in physical science before, so I didn't know if you. We'll do it this chapter, okay? Now, something that we've got to get good at here is knowing what conjugate pairs are. And I kind of started briefly beginning to show you this a second ago. What I'm going to do is write an equation up here, and we're going to talk about this. So you're going to want to write this somewhere with space to write stuff underneath it / above it. Find a spot. Ideally, if you can put it near the conjugate acid-base pair, that would be great. Hooray, this thing okay?
Okay, what?
Yep.
What?
What?
Did you understand what he said?
Who?
Me? Yes, he did. Of course.
I didn't even hear him.
Yes, he did.
What?
When I just yawned and I said, did you have to write this whole thing down? He said, yeah.
Oh.
How did you understand that?
I understood it.
Aw, shoot, I messed up.
Time. Now, this slide, I think, kind of makes it a little bit confusing. It says, if something loses a proton, what it turns into is called a conjugate base, and I will explain what I mean. There's a better way, I think, if I go like this and give these two definitions. It might make a little bit more sense, and then we could go back and go to those other two slides and be like, okay, I get it. Okay? First and foremost, I haven't done a ton of this stuff with you yet. I have defined what an acid and base is. Can you figure out by looking at this, going in the forward direction, which one of these two acts as an acid and which one acts as a base? Okay, the H2O acts as the base. Why do you say that?
Because it gains hydrogen.
Okay, so from here to here, it accepted, right, a proton, making it a base. Okay?
And that one.
Well then, therefore, if this is the base, it's probably the acid, but let's just make sure, from here to here, what did it do? Lost, so we would categorize this as an acid. Okay? Now notice, it says, I'm going to connect these here. A conjugate base, let's read its definition. It says the structure formed when an acid is deprotonated. What did I say? Or I guess I didn't really talk about it, it was in your notes. What do you think deprotonation means?
Losing a proton.
Losing a proton, okay? So, when an acid loses a proton, the structure that remains is called a what?
Conjugate base.
Conjugate base. And I'll explain why we call it a conjugate base here in a sec. Just using the definition to define it. And then I'll tell you why we can even call it a base. Okay? A conjugate acid is the structure formed when a base gets protonated. So this base got protonated, making it a conjugate acid. Now let me show you why. What was that?
So went from a base to an acid.
Yep. Now listen, I would call this a conjugate acid base pair, and I would call these two guys conjugate acid base pairs. Here's the thing that you should notice. All conjugate acid base pairs differ in one proton. What's the only difference between these two guys? One proton. What's the only difference between these two guys? One proton. So conjugate acid base pairs only differ in one proton. Now let me explain why this is an acid and this is a base. What does this mean? Reversible. So if I go from right to left,
That one's gonna get.
this gives, which makes it a what?
Acid.
Acid. And this accepts, making it a base. So you're going to find out that in this chapter there is equilibrium between acids and bases in their reactions. Okay? And that actually helps us define whether an acid is strong or whether an acid is weak. A strong acid is an acid that breaks apart completely and lies far to the right. A weak acid is one that doesn't break apart very much, and therefore we would say it lies far to the left for equilibrium. But we'll get into that when we start defining strong and weak later. Okay? Questions on figuring out conjugate acid-base pairs and why we can call this an acid and this a base. Any questions on that? Okay? What's the key here though about conjugate acid-base pairs? They only differ in
One.
one proton. And that proton is your positive decharged hydrogen. I think this is saying, yep, there you go. All right, how does spontaneous differ from the Bronson-Lowry? To
Base definition.
base definition. Spontaneous says it gives off an OH minus. Bronson-Lowry says that it gains a what?
Or donated.
All right. Woo. What is the Bronson-Lowry base in this reaction?
Well,
Yeah.
the base is going to be H.
Yeah. HSO4.
HSO4.
As HSO minus 4.
No, 3. Looking from here to here, it did what? Gained a proton. That's the definition of base, right?
And
So
Oh.
there's actually 2 here.
technically Cl minus.
Technically, this is a conjugate base, so we could say 2.
I said CL.
Okay.
Yeah,
But usually, if I ask you what the acid or base is, I'm usually asking you the Ford reaction's acid or base. Does that make sense, everyone?
I said CO.
Did I confuse you guys?
One is the conjugate base or acid, you just say what's the conjugate base or acid?
Yeah. I would, if I wanted you to find out what the conjugate acid or base was, I would specifically say, what is the conjugate acid? Or I would say, write the conjugate acid base pairs. Okay. All right. Here's the last definition. Okay. And we will probably use this one the least, even though it is the one that best classifies all acids and bases. There was limitations in the first definition because you could have a base that didn't have OH minus in it, right? The second definition has some limitations in that sometimes it doesn't appear that a proton has been given or taken. I know this is last definition. Okay, the next, the big chart is just summarizing everything for you. Okay? So let me give you an example. I'm going to write it like this because in order for us to see this, we have
Oh,
to,
Lewis structure.
we have, yeah, that's why they're called Lewis acids and bases. Okay, so I'm writing it like this so that we can see our electrons.
I forgot these existed.
What? Don't say that.
Is it actually called Lewis structure?
What else? Yeah.
Or
What?
Louis? Yeah, I always thought it was just the Lewis structure because it just calls the
Don't leave.
acid.
I'm almost done here. Now, could we have defined this as the base and this as the acid using the Bronson-Lowry method?
Yes.
We could have, right? Given a proton, taking a proton. Okay? But here I want, so we said this is the base, this is the acid. And here's how they look at it. Okay? Going from, let's look at the definition of Lewis acid. Accepts a pair of electrons. So, an acid goes from here to here. 3 pairs, 4 pairs. So it's basically the opposite of giving a proton. If you give a proton, you're left with excess electrons. It's really much more complicated to understand, and the reason why we're not going to spend much time talking about it is it pretty much just allows you to define a small handful of acids and bases that aren't really commonly used. If you want to define it, so what you will have to do or know for a test is just know the definition. I'm not going to make you apply it or anything. I just want you to have seen it so that if you do become a, you go and get your doctorate in acids and bases, you were like, hey, I remember Mr. Kramer at least talking about it. They probably have some name for that.
Acidologist.
I have a PhD in acid.